All right, so this talk is the case for declarative machine learning. My name is Tristan Zients, and to kick things off, who am I? So that's me. Look better there than here. I built one of the first enterprise data science platforms called Sense.io. Some of you that are a little bit older and have gray hair might remember it, but it was one of the sort of early notebook platforms that were moving everything to the cloud and supporting Python and R and all that sort of stuff. That company got acquired by Cloudera, and I built the machine learning platform for Cloudera, which is the big data Hadoop platform. And I'm currently the co-founder of Continual. And I say that only because this new project is really based on all the mistakes and pain and suffering that I had from this previous 8 years of my life. So it's another way of saying I'm basically a hypocrite. This is a talk that I gave in 2018 at the Kubernetes KubeCon, which is how to do machine learning on Kubernetes and why it's so amazing to build pipelines on Kubernetes. And as you'll see, I'll critique that approach here a little bit. Or maybe it's just that there's let's go beyond that, right? We've done that for 5 years. Let's do something new. So starting thesis is that ML ops is drowning in complexity, and I think for anybody who's working in the ML ops ecosystem, hopefully that says, well, I like my tools, but yeah, they are pretty complicated. Okay, like maybe they're really powerful, but they are pretty complicated. And I think if you trace this back, I think a good example of this is 5 years ago there was a blog post by Uber where they described their internal machine learning platform, the Uber Michelangelo platform. Actually, an amazing architectural vision for what production machine learning looks like. By production machine learning, I mean models that are actually driving businesses decisions that are continually maintained, right? Not just a notebook, not just an R&D project. And so in their case, they wanted to do that canonical Uber thing. They wanted to predict the arrival times. That's what the business needed. And they said, okay, here's the stack that they built. And if you look at this stack, you can see there's about 7 different distributed systems here. This is Kafka, right? That's like a whole bunch of nodes. That's your storage, Spark streaming engine. There's Cassandra, which is your operational database. There's a serving system over here. There's a client. Oh, there you have a data lake or a Hadoop cluster. Batch. Well, you have Hive. I guess Cassandra. No, you need different storage. Hive. A whole bunch of things here, right? A lot of stuff. So incredibly powerful. If you're an ML engineer, it's kind of fun to build for the first time. I spent my last 8 years doing this kind of stuff, but it's complicated. It's complicated. Then you say, okay, we will move to the cloud, right? Google solved this, AWS solved this for us, right? So here's AWS's stack diagram I just Googled like operational machine learning for AWS, and like this is the way they told me to do it. I'm not exactly sure how that all works, but it does. I'm sure everybody here is smart enough to make it work. I'm actually sure it probably does work, right? And then, oh no, we're all startup folks, right? So let's do the startup thing, right? Let's actually, the AWS doesn't invest much in their individual tools. Let's be like best of breed tools. And man, there are amazing tools today. Amazing notebook products. They're amazing experiment trackers. I mean, it is remarkable. That has certainly changed. There's some awesome individual tools. But to go to production ML, it's quite hard when you think about continually retraining, continual inference, monitoring the whole life cycle of it. It gets pretty tricky. And what it means is you just won't use. What does it mean? Okay, so what's the end result of this? I think 3 things. One is infrastructure challenges. This infrastructure is just extremely complicated to set up, to maintain. It's often disconnected from the rest of your data and analytics infrastructure. So there's sort of honestly a developing parallel universe in the ML world compared to the data and analytics world. We probably have some people that are more in this modern data stack world. Some people are more in the ML world. It's 2 parallel universes, right? So just a lot to manage. There are team challenges. The only people that can do this, right, are you got to be a cloud engineer, an ML engineer, a data scientist, a product engineer to actually implement an end-to-end use case, right? Which just means it just requires a lot of time. Even if you have the skills, it just requires a lot of time, right? And you kind of, after you've done it once or twice, you maybe don't want to spend the next 3 months building that next use case and then being on the hook and on call to support it. And then the final one is this operational challenge, right? You've got to get to production. Anything that's actually going to impact the business, it's got to be maintained, it's got to be governed, it's got to be monitored, and you got to, you're on the hook. Who wants to be on the hook for things that are that complicated? And of course, then it seems like most people leave and start a startup who build ML platforms at a company. So you actually got to join somebody else's ML platform and support somebody else's ML model. So it's just less fun, right? Not super fun. Okay. So the question is there a better way? That way has been the sort of the status quo way for the last 5, 6, 7 years. Everybody's building it. It's extremely powerful. It's I guess you could say it's proven. But the question is there another way? And I want to say there is another way. we've seen this problem before, and we've actually fixed it in other domains. So, and remarkably, actually, Sandy, I don't know if Sandy's here, but he gave almost exactly similar slides yesterday at the Dagster. Sandy gave us similar slides at the Dagster talk, so shout out to that. It's amazing that we converged on the same slides without seeing each of it. So, what do I mean it's been solved in other domains? So think about infrastructure. We used to manage infrastructure with bash scripts. We'd provision things. We'd call AWS APIs. We had APIs, but we managed it with bash scripts. Who does that anymore, right? We use Terraform, right? Or we use Pulumi. We use something that has moved from this pipeline jungle world to some sort of declarative specification here with Terraform. Think about data, right? You might remember, we all got excited about MapReduce. We wrote all of these crazy MapReduce jobs. Now, what's the new reality? We're back to SQL, right? We're back to a declarative high-level language that allows us to do analytics. Or if you want to go beyond SQL, go and use Dagster. Even Dagster is moving to a declarative sort of way to manage data assets and allowing you to have the flexibility of code or Python to do it, but still automating as much as we can and removing it. If we think about UI frameworks to go a little bit further afield, right? We used to all build UIs. jQuery was, oh my God, it standardized the DOM for those who are UI people. And then what do? We use React, right? Top-down state. Everything's a component. Don't have to worry about how the DOM gets updated, right? It's just a declarative way to build UIs. Doesn't mean it's code-free, right? Doesn't mean it's no code, point and click everything. But it's saying let's get rid of all the incidental complexity that we don't have to care about. That's not substantive to the problem at hand, which is building a UI or whatever it is. Let's get rid of it, right? Build a higher level abstraction if we can find one. So that's the solution, it seems, in many domains, is to find the right higher level abstraction. In some ways, the future of technology always has been moving up the stack, right? From hardware to higher level of software abstractions, right? To garbage collection, et cetera. Now declarative systems. So the question I have for everybody is, is there something similar that we can do with respect to ML, whatever domain of ML that you might be working on? And what we're working on at Continual is to enable operational ML. Is there a way to find a higher level abstraction that simplifies this, that democratizes it, that makes it easier to put into the business? And okay, is there? So I think the first thing to say is, well, what is operational ML? Like, how do we decompose this? Can we find a pattern here? Well, so the standard answer is, if you actually know how this works, is it's basically pipelines, right? There's all these pipeline jungles to maintain all these things, to maintain models, monitor models, retrain models, rescore models, et cetera. That doesn't seem like it works, but that doesn't seem necessarily like the right approach, right? That's kind of the imperative approach. So I want to submit that there are really two things. There's one thing with respect to ML, and then there's another thing with respect to operational side of the things. So the first thing with respect to ML is the task. At the very high level, we need to describe the task. What are we trying to predict? What are we trying to achieve? Not the algorithm or how we're going to do it, but the task, right? And there are, if you start to squint carefully at where the state of the art is going with respect to ML, a very high way to think about tasks as inputs, okay? What are going into your predictive models, and what are coming out of those models. And you can think of the different types. So think about classification. So here I have a diagram. This is from this Ludwig project, which is super interesting. A diagram where I have a bunch of input types going to output types. And we have, let's say text to text. Well, that's, OpenAI's whole business model right there. That's machine translation, right? So if you had text in, text out, that's machine translations. If you had a categorical and a number going to a number, that's regression. If you had category to a number going to a category, that's classification, right? If you have time series sequence to a time series sequence, that's time series forecasting. Image to a category, that's image classification. Image plus text to text is image question answering, okay? A sequence and a sequence to a sequence can actually be reinforcement learning. You can actually have a sequence of states, a sequence of rewards, conditioning on the rewards, and then generating the sequence of actions that you're doing. So you could actually play chess with this. A bunch of papers actually this year about this, how you can think about reinforcement learning as a sequence problem. So the point is, all this is input types, semantic input types, rich input types. You might need a broader range of types mapped to output types. And you can describe an incredible range of ML problems. And who cares? The algorithms, is it deep learning? Is it XGBoost? Well, the internal system can figure that out, right? Maybe this is all should be done with one kind of new transformer model. There's incredible convergence, or maybe we should just do AutoML, try a whole bunch of things, see what works, okay? The next thing is, well, that's just the model. What about operational? We need to think, we're going to maintain these model monitors. What do we actually need to know? And so that, I would say, we need policies. We just need a few different policies, things like, and here's a screenshot from Continual, where it's our UI, building the UI, the policies in the UI. We support different ways to do this. And we have, okay, we're going to train this model monthly. We're going to promote the latest model or the best model, or we're going to manually go in there and promote the model. we're going to rescore their model and kind of update the predictions in our world in the data warehouse, as you'll see. We'll do that every night, right? We're trying to update the churn and maintain the probability a customer will churn or how much they'll spend or what your inventory level will be. We just set some policies. And so we just need tasks and policies. What else do we need? Why isn't everything else just automatic and taken care of for our platforms? So that leads to Continual, right? This is a startup. I guess this lightning talk is kind of startup oriented. So what are we doing at Continual? So we're trying to take this desire for building a higher level abstraction for ML, and we're bringing it to the modern data stack. So Continual, Continual.ai, we're building operational AI for the modern data stack. There's 3 fundamental things that we're doing. So the first thing is that we're data centric, but more importantly, we're data warehouse centric. So we believe that the future of data lives in the data warehouse. We both read the data from the data warehouse and write the predictions back to the data warehouse. So you can think of us as continually maintaining predictions and enriching your data warehouse with predictions. 2, to this talk, we have a declarative workflow, right? There's no infrastructure, there's no pipelines, there's no models. Everything can be done through a declarative data-first specification. And I'll show you exactly what that means in a second. I have no idea what my time is here because there's no timer. And we're 3 minutes. Okay. And when we're operationally focused, in that sense, everything that we build in Continual is maintained. We maintain the models and we maintain the predictions. And so, what does this look like more specifically? So, in the data warehouse, DBT is very popular. And so, what we want to do is we want to enable different types of users: people that want to use a UI, people that want to use DBT, people that want to use YAML, people that want to use Python and declare things in Python. So let's imagine that we're the DBT user. What does this look like? Well, the first concept we have is the feature set. This is our inputs. What are the inputs to your predictive models? What do you know about your customers? For instance, how active have they been on your website? How much have they bought? These are the inputs to your predictive models. So we say the first thing you need to do is register in the system in a declarative way the features from the data sitting in your data warehouse. Now, if you're using DBT, this looks very familiar. You have a SQL query. This is a DBT. This is the way DBT works. It's DBT SQL query plus DBT annotations. If you want to think of it as a YAML file, it's exactly the same thing. If you want to think of it as a Python function, you could do that with a bunch of inputs or JSON or whatever you have. We augment it with a couple things. We say that there's an entity. This query, customer ID month, feature 1, feature 2, from this customer activity table, relates to my customer. I need some semantic information. It's about my customer. Not just saying my index, my customer ID references my customer. Then there's a time index. It's super important for machine learning use cases to take very careful attention to time. And so here we have a time index, which is saying that this feature is for this particular moment in time. What did I know about the customer at this particular moment in time? So that when I predict whether they're going to churn, I'm using the right information that I had. I'm not leaking information, right? So we register this with our system. Now we have features that we can use in a lot of predictive models. Second thing we need to do is actually need to build something that's predictive, okay? For that, we need the outputs, right? What are we trying to predict, right? So that the ground truth that we're going to try to predict. And I guess it's a little bit more complicated in terms of the metadata, but from the query, you just have the customer ID of the month and the churn. In this case, it's whether the customer is going to churn the next month. Then you can define, again, a little bit of extra metadata, the index and the time index, just so you have that link, that join, essentially. The target, what are you trying to predict, right? And then here we have a foreign key reference, essentially, that this customer ID column references this so that we can join in the right information at the right point in time. So with a point in time correct join, so we don't have data leakage, we can join this in, and a little bit of policy around how we want to maintain this. From this, we should be able to, in my view, we should be able to drive a production ML system that is continually maintained, continually updated. And that's what happens in Continual. So, this is the model that you get. Like basically, this is a visual representation of what I just showed you. It's actually from the product. If you were using the CLI and not the UI, and you're a DBT user, you'd run DBT run, which generates your views in Snowflake. And then you'd run Continual run, which generates a number of tables and views inside your data warehouse where all of your predictions are going to live and be continually maintained, right? From that with nothing else, okay? What happens when you do Continual run is we, like Terraform, go and figure out what needs to happen. We figure out, do we need to create some tables and views in your data warehouse? Do we need to train some models? Do we want to profile things? Do we want to run a prediction and update the predictions in your data warehouse? We can figure all of that out from that declarative specification. So here we're creating some views. We're running a bunch of models. We're looking at the particular model type, which in this case was classification. And so we realized that we tried a whole bunch of 11 different experiments. And we've got this model. We promoted a model, and we predicted it. This is like a Terraform apply plan, if you think of if you're from that world. Here's the example of us. Hey, we're doing classification. Let's just try a whole bunch of models, right? So AutoML, let's try this. And hey, if you want to have drop down and extend it, fine, extend it, right? But that shouldn't be the aspiration, right? So you get 97% accuracy again with almost no work. And then, of course, it's got to be in production. It's got to be monitored, right? Otherwise, you're not having an impact. And so, again, all I did was add some schedules, and now the model is continually maintained, retrained, re-inferenced. We get historical performance, current performance, a whole bunch of other stuff, drift, etc. So here you are. Let's build more declarative ML systems, regardless of the domain you have. It powers your whole data team. It reduces the operational burden of ML, and it's just way, way more fun. So Continual.ai if you want to check it out.